This screencast covers everything you need to know to get started implementing REST services in Go. We'll see how to use Go-based REST services to access a Postgres database. One reason to use Go is that it is a fast server-side programming language. Implementing REST services is currently the most common kind of server-side development. We will use Postgres because it is a very popular open-source relational database. The Go programming language is simple compared to many other languages that have much larger specifications and support many more features. The Go compiler is very fast, and Go programs have good performance compared to other languages. Go is a statically typed language which helps in finding many code issues at compile time. Go is also a great language for applications that require concurrency or parallelism. There are many free resources available for learning Go. Several are listed on this slide, including links to some for articles I wrote about Go that cover everything you need to know to get started and all the syntax details of the language. There are many open-source Go libraries that support implementing REST services. Some of the most popular ones are HTTP Router, MUX, and Gin. We'll focus on Gin and use the go get command to install it. We will implement REST services that manage a collection of dogs stored in a Postgres database. These services will handle the common CRUD operations to create a dog, retrieve all the dogs, update a dog, and delete a dog. There are several open source Go libraries that support working with Postgres databases. We'll focus on PQ, which is a popular choice. Use the go get command to install it. The dog database has 3 columns: the unique ID, breed, and name. The DDL to create this table is shown here. We will assume that the web application that uses REST services is served from a different domain. Since browsers disallow sending HTTP requests to a different domain by default, we'll need to enable cross-origin resource sharing, or CORS, in the REST services. This is done by including specific response headers. One of these determines the domains that are allowed to use the REST services. We can set this to an asterisk to allow any domain or specify the allowed domains. We'll allow just one specific domain to access the services. We can also restrict the HTTP methods that are allowed. We will allow GET, POST, PUT, and DELETE requests. When browsers are preparing to send a POST, PUT, or DELETE request, they first send an options request to verify that those HTTP methods are allowed. This is called a pre-flight request. To support this, we have to include processing of options requests. Look for this in the upcoming code. Implementing CORS is just a matter of including the right HTTP response headers. The headers listed here are the ones that are commonly included. Notice that their names all start with access-control-allow-. Origin specifies the origins that can invoke a service. Methods lists the HTTP methods that can be used in requests. Headers specifies request headers that can be included. Some common headers are accepted by default. These include accept, accept-language, and content-language. Others must be listed. The content type header must be specified in order to accept requests with JSON bodies. Credentials is only needed for services that require authentication. Let's jump into the code. All the code on the next 13 slides is in the file main.go. Each slide covers a specific piece of the functionality. Here we see the Go packages that are imported. The first 6 are part of the Go standard library. The database/SQL package is used to open a database connection. The errors package is used to create objects that describe errors. The format package is used to create SQL statement strings. The log package is used to output a fatal error if we cannot connect to the database. The net/HTTP package is used to get HTTP status constants for OK, bad request, forbidden, and internal server error. The string convert package is used to convert between string and int values. The gin package is used to handle HTTP request routing, so each kind of supported request can be handled by a different Go function. Finally, the PQ package is used to send SQL queries to the Postgres database. All the constants used in this file are defined here. The first specifies the only allowed origin that can send HTTP requests to this server. The rest define constants that provide a more compact way to refer to the HTTP status codes that will be used. Each dog will be represented by an instance of the dog struct. We will pass objects of this type to functions in the gin package, so the fields need to be exported so it can access them. Names in Go are exported if they begin with a capital letter. We will also need to create JSON representations of dog objects. It is typical for JSON properties to have names that begin with a lowercase letter. The strings and backticks that follow each struct field are called struct tags. They provide details to functions that act on the struct. In this case, they provide alternative names that can be used when these objects are converted to JSON. We could use Go libraries like the one mentioned at the top of this slide to handle all the core's details for us. But as we will see, it's pretty easy to do without a library. There are two places in the code that need to verify that a request came from the allowed origin. That is determined by calling our shouldAllow function, which gets a request origin from a header that it obtains from the gin context object that is passed in. Many server-side web frameworks support the concept of middleware. This makes it easy to specify code that should be run on every request. The cores function will be registered as such a middleware. It verifies the request origin of every request. If it is allowed, the function sets the response header access control allow origin to the allowed origin. Otherwise, it sets the HTTP response status to forbidden. Note that we could allow any origin to invoke our services by setting the access control allow origin header to an asterisk. Recall that post, put, and delete requests are preceded by a pre-flight options request. We need to support two options request paths. Both need the same logic, which is to set the headers shown in the options function here and set the HTTP response status to OK. Putting this code into a function allows the two options routes we will see later to share this code. The headers that are set in the options function are only needed in responses to options requests. To simplify error handling a bit, we define the handleError function. This sets the HTTP response status code and adds the text message found in an error object to the response body. Now we are ready to begin the definition of the main function. This is where execution of a Go application begins. The first thing we do is obtain a connection to our Postgres database. If we cannot connect, the application terminates with an error. Continuing on in the main function, we create a gin router that will handle all the incoming HTTP requests. Then we tell it to use our cores middleware function for all requests. The two options routes here are invoked before post, put, and delete requests. The reason we need two is that the post requests do not include an ID in the URL path, but the put and delete requests do. Finally, we define a route for get requests to /. This provides a simple way to verify that the server is up and working. It just returns the string, I'm alive. Now we are ready to define the main services. We'll start with the REST service to create a new dog. This is done with a post request that includes a JSON body that provides the breed and name of the dog. We use the shouldBindJSON method of the context object to parse the JSON body. If there's an error in doing this, the processing stops and a bad request status is returned. Otherwise, we create and execute the SQL statement that will insert the new dog into the database table. This will assign an ID to the dog. We copy that into the dog object and return the dog object to the client as JSON so it can use that ID later to update or delete the dog. This route is for retrieving all the dogs. Since it is invoked with a GET request, there will be no pre-flight options request. This means we will not have verified the request origin yet, so we do that here. Then we query the database for all the dogs. That gives us a rows object that must be closed when we are finished using it. Go has a nice feature for doing this sort of thing called defer. It takes a call to a function that will not be executed until the current function is ready to exit. Continuing on in the same function, we iterate through the rows, creating a dog object from each row and add it to an array of dog objects. Actually, we add them to a slice. A Go slice is similar to an array. One of the ways in which they differ is that a slice can grow, whereas an array retains a fixed size. Finally, we return the slice of dogs as a JSON array in the response body. This route is for updating a dog. It gets the ID of the dog to be updated from a path parameter. This should be an int. If it is not, a bad request HTTP status code is returned. The request body should contain a description of the dog being updated. Both the breed and the name can be modified. If the body does not contain the expected JSON, a bad HTTP status code is returned. Continuing on in the same function, we create and execute the SQL statement that will update the dog in the database table. If this is successful, an OK HTTP status code is returned. This route is for deleting a dog. Like in the update route, this gets the ID of the dog to be deleted from a path parameter. Then we create and execute the SQL statement that will delete the dog from the database table. If this is successful, an OK HTTP status code is returned. Now that all our routes are defined, we start the router. It just needs to know the port on which it should listen. This is the end of the file main.go. There are two ways to start our server application. During development, it is convenient to use go run main.go. This builds and runs the application. For production use, it is better to build an executable that can be run any number of times without recompiling. The command go build main.go does this. The resulting executable can be run like any other executable. Here we see the initial output, which lists all the routes we have defined, including their HTTP method and path. One way to test REST services is to use the free version of PostgreSQL, which is available at the URL on the screen. This supports creating HTTP requests, saving them in catalogs, and executing them. Here's a sample of the PostgreSQL UI. In the left nav, we see a list of catalogs. I've created one called Go Server. It contains the definitions for 5 requests that exercise all the features of the server, including the heartbeat service. We can select a request, optionally modify it, and press the Send button to send it and see the response. During development of a server, it is useful to have something watch files for changes and automatically rebuild and restart the server when changes are detected. The gin package supports this. It is not the same as the gin package used to implement REST services, just an unfortunate name collision. To use gin to provide watch and live reload, follow the steps on this slide. We need to tell it the port on which the server is listening, 1919 in our case. Gin acts as a proxy for requests. By default, it listens on port 3000. So requests sent from web UIs and from PostgreSQL need to be modified to go to port 3000. That's it. You now know everything you need to get started implementing REST services in Go. Thanks for watching. For details on OCI events and training, see the URLs on the screen.